So we come to the very important part of the first law of thermodynamics and applications today. After having discussed about Maxwell's distribution curve and most probable speed and mean speed, etc. in the last lectures. So I'll just quickly go through a recap of that and we will begin with today's session.
Sir, we were remaining with the average speed one.
Yeah, we have to discuss the formula of the mean speed now. Most probable speed I told you about, right?
Average also.
Yeah, most probable we had discussed, right, with the Maxwell's distribution.
Yes, sir. We had discussed that.
Yeah.
Yes.
Just one additional formula is there for most probable, I mean for average speed. So let's come to that. Yeah, so a couple of queries here that I'm receiving. First of all, from H.C. Verma, if you look at the kinetic theory of gases chapter, there are some additional concepts of vapor pressure, saturated vapor pressure, humidity, and dew points. So that has to be excluded because that is not part of your JEE syllabus. You can go through the explanation of all those things from the H.C. Verma theory part, but it will not be required for your JEE. For your JEE, the important thing is just going to be the application of the formula we've discussed so far from kinetic theory of gases. So I'm just doing a recap of the early formulae that we've discussed first, and then I'll come back to the mean speed and all that. So this is what all you have to know from kinetic theory of gases as part of your heat and thermodynamics. So as part of kinetic theory of gases, you have to first of all know the assumptions of the kinetic model. Okay. Including the explanation of Brownian motion. Okay. So along with that, you get the derivation and application of this formula. So sorry, small n into capital M. Okay. Next, you look at the kinetic interpretation of temperature. So from that you get that PV is equal to nRT, or PV is equal to capital N KT, and putting that back in the above equation, you get RMS speed in terms of temperature, in terms of absolute temperature. Okay. So these two formulae actually become the most important: the ideal gas equation and its applications, and the RMS speed in terms of temperature and mass, molar mass, etc. Okay. Next, we come to equipartition of energy. Okay. And degrees of freedom. So in that, the important concept is the average kinetic energy per molecule per degree of freedom. That is given by 1/2 kT. Okay. So therefore, from that we get the average kinetic energy per molecule becomes F/2 kT, or you can say that the average kinetic energy per mole becomes F/2 RT. Okay. And from that we get the concept of the internal energy of an ideal gas. That becomes F/2 nRT, or that's the same thing as F/2 into pressure into volume. So now these formulae become very important: the concept of internal energy the concept of average kinetic energy per molecule per degree of freedom. You know that if you can see that if you're clear with all these concepts, then you should be able to solve any and every question related to kinetic theory of gases in your JEE syllabus. Okay. Additionally, of course, you should know the standard values of degrees of freedom. It is 3 for monoatomic gases, and it is 5 for diatomic gases. Whereas for polyatomic gases, you don't have to know a specific value. You should just know that F can be 5, 6, 7, etc. for polyatomic, as may be the case of a particular molecule. So that's some additional facts that you should know. And now in addition, so basically these are going to be the important things. Now just for your JEE mains type exam, there are two additional formulae, which is the formula for the most probable speed, okay, which is square root of 8 RT by pi m, was it?
Yes, sir.
So this is, if you look at the Maxwell distribution curve, this value of velocity at which the probability is maximum, that is called the most probable speed. So this is not a very important formula in terms of further applications, but it's something additional that you should know for direct formula based questions. And along with that, there is also a formula for what is called mean speed, mean or average speed of gas molecules. So that is, we denote it with this symbol. This bar means mean, and that is given by square root of 2 RT by m. So apart from the value of RMS speed, which you can see over here, there are these two other types of statistical quantities which become important as part of the Maxwell distribution curve. I'm not writing the formula of the Maxwell distribution equation, the probability density, because it's not important, okay, from your syllabus point of view. I've explained about it in the last lecture, but okay. So everything that you require from kinetic theory of gases as per your JEE syllabus is more or less contained in this page. Okay. The main thing is going to be the application of these concepts in first law of thermodynamics, which we will see next. Okay. So now we will move on to the next section, which actually, I mean, for whatever reason, it's a separate chapter, but it's like a continuation of this concept of kinetic theory of gases only. Okay, and that is the application of the kinetic model of an ideal gas, including the formula of internal energy, into thermodynamics. Okay. So all this you have noted down before, so don't need to refer. Okay. So now let's come to the next section, which is the first law of thermodynamics and its applications. So before we come to the statement of first law of thermodynamics, let us understand what is meant by a thermodynamic process. Okay. So a thermodynamic process,
सर वो ऊपर का नोट नहीं करना था.
not necessary, just you can note down the formula of the mean speed. That was the only new thing. The rest of the things I've just summarized what we've discussed before. I'll be sending you the notes now, so don't worry. Okay?
Yes, sir.
Okay. Okay, so first of all, let us understand what is a thermodynamic process. Okay. So a thermodynamic process is a process in which the state of a system changes due to exchange of heat and or whichever be the case mechanical energy with its environment. Okay. So this is the broad description of a thermodynamical process. So this covers, literally any process in the physical universe which involves this kind of situation where mechanical energy and heat is being exchanged or heat is being exchanged, and as a result of that the state of some system is changing. So it could be a process happening at the molecular thermodynamic level. It could be a process like a very artificial man-made process like what is happening inside a heat engine. Okay. Or what is happening in a chemical reaction, for example. So there's thermodynamics involved in a chemical reaction also, because as the atomic structure or the intermolecular structure of chemicals is changing because they are interacting with each other, there is an exchange of heat and there's an exchange of mechanical work. So there's a thermodynamics involved of chemical reactions also, which is, as you know, is called chemical thermodynamics. Okay. But in our chapter in physics here, we will apply this to a more specific situation. So in this chapter, so in this section, what we will study, okay, we will look at thermodynamic processes for an ideal gas. Okay, so an ideal gas is a gas that is described by its state. That is, the state of the gas is given by pressure, volume, and temperature. Okay, and the equation of state, which is PV equal to nRT, the ideal gas state equation. So we will restrict ourselves to only those type of systems. Okay, in general thermodynamics, a thermodynamic process is a process due to which any system, okay, changes its state because of this. But here we will restrict ourselves to thermodynamics of an ideal gas. So the state of an ideal gas is given by pressure, volume, and temperature, and the equation of state is given by PV equal to nRT, because it's ideal gas, so it is behaving according to the kinetic model of the ideal gas. Okay. So according to such an equation, such a situation, the first law of thermodynamics is a statement that the net heat supplied to the gas during the thermodynamic process is equal to the change in its internal energy plus the work done by the gas. Now you might have seen this equation in a slightly different form in chemistry, so don't get too upset if that's the case. I'll explain to you why it is different and how it is different. So according to this statement over here, Q is defined as the net heat supplied to the gas, not by the gas, okay, to the gas during the given process. Okay. Delta U is the change in internal energy of the gas. Okay, and again in this U is nothing but the total kinetic energy of gas molecules. Okay. So from kinetic theory of gases, we've seen that the formula of internal energy is F by 2 nRT. So that is what we'll very much be applying over here, because we are dealing with that kind of situation. Okay. And W, the third term, is equal to work done by the gas. This is the net work done by the gas during the process. Okay. So we have to emphasize that W is, we are talking about work done by the gas, and Q we are talking about net heat supplied to the gas. Okay. So when we further break this down into mathematical equations, it will become more evident. Okay. What is the meaning of these terms, etc. So just write down the statement of first law. Okay. This equation is called the first law equation, okay, or the first law of thermodynamics itself in equation form, that in any thermodynamic process, the net heat supplied to the gas equals to the change in its internal energy plus the net work done by the gas. Okay, this is the form in which we write it in our physics syllabus over here. We write it in a slightly modified form in chemistry, but ultimately both are the same. So just make a note of this first, people.
Sir, can you explain once again, please?
This is just, there's nothing further to explain. It's a logical statement that in any process, the net heat supplied to the gas, it will be equal to the change in its internal energy plus the work done by the gas. Like we write the statement of work energy theorem, that net work done is equal to change in kinetic energy plus change in potential energy. Like that, it's a statement of energy applied to a gas.
Okay, sir.
Okay, now let's understand each of these terms. But before that, we can also write the first law in such a way that Q plus, but we'll call this term W prime instead of W, is equal to delta U. So if we write it in this form, W prime will be equal to the net work done on the gas, not by the gas, during the process. Okay, so there's no difference between the two statements really, because the net work done on the gas is equal to nothing but, sorry, net work done is on the gas is nothing but negative of the work done by the gas. So they are ultimately one and the same. Just a matter of choice how we choose to write it. Do we write it in terms of work done on the gas or work done by the gas? So in physics, we write the statement as the first one, where W is the work done by the gas.
Sir, what is zeroth law?
Sorry, what is?
Zeroth law.
Zeroth law, that is the law of calorimetry actually, that the net heat supplied, net heat lost is equal to the heat gained when there is transfer of heat from a body at lower temperature to higher temperature.
Okay.
Actually, that is the statement of zeroth law. Zeroth law, that is the application of zeroth law. Zeroth law statement is more like this, that when two bodies come in contact, then heat flows from the body at higher temperature to lower temperature till they come to the equilibrium temperature. That is the same temperature. So it's a very logical statement which you've seen before also at 9th, 10th.
Sir,
Yes.
sir, the first law can also be expressed as the energy created is neither or nor can be destroyed, no?
Yeah, in the sense that if you include the entire energy of the universe, that is the environment of the gas plus the gas itself, then energy is neither created nor destroyed. All right, is it clear?
Yes, sir.
But we don't need to think in such complicated terms over here. We will just apply it to simple situations where we are compressing or expanding the gas, or we are heating it, or we are cooling it. And we'll see that it's basically just a matter of exchange of heat and energy, that is mechanical energy, between some kind of external agent, which you can think as the environment of the gas and the gas itself. So yes, in that sense, that the sum of heat and mechanical energy remains conserved. It's only getting exchanged between two things. One is the system, which is the gas, and the other is its environment, which is the external agent. Okay, now in this, let's understand each of the terms more carefully.
Sir,
So,
1 minute.
okay.
Done, sir.
Oh, so in this U, as we have seen, is the internal energy of a gas, which is nothing but it is the total kinetic energy of its molecules. Okay, so that is equal to NF by 2 RT, or F by 2 times PV, because PV is equal to nRT. So we can see that the internal energy is what we call a state function. Okay. Internal energy is a state function, that it's the value of it depends only on the state, that is pressure, volume, and temperature of the gas. Okay, therefore, we can say that delta U, which is final minus initial internal energy, it can be written as NF by 2R into final temperature minus initial temperature. So that means the value of delta U, the change in internal energy, is what we call path independent. It only depends on the state. depends on the final and initial states of the gas, not on the path or process taken from initial to final position. Okay, so this is something very important over here. So to visualize this better, we can also think of representing the state of a gas on a PV graph. Because any point on a PV graph, not only it has a particular value of pressure and volume, but it also has a particular value of temperature. So if I have any point like this over here, which is the point A, then that point A has a particular pressure, it has a particular volume. So it also has a particular temperature, because the three variables are connected in this. Now think of any other point. Okay. Just for reference, I'm showing it as a point having a larger pressure, a larger volume, and therefore a larger temperature also. But it could be less also, it doesn't matter. Okay. Two distinct points. So now what is happening is that as far as if A is the initial state and B is the final state, I could go from this state to this state via some kind of path like this, which would represent a particular thermodynamic process for which the initial state is A and the final state is B. I could go by some other path also like this, let's say. Okay, so this is path 1, this is path 2. But whether I go by path 1 or path 2, the value of delta U will be the same. Okay. So here we understand that the state of any gas, PV and T, can be represented as a point on the PV graph. Okay. Example, the point A which I've shown, or the point B which I've shown. Those are 2 points at which the gas has 2 distinct states. That is, it has distinct value of pressure, volume, temperature. It has distinct value of pressure, volume, temperature. Okay. No 2 points, no 2 distinct points will be such that all the 3 things are the same. That is, pressure, volume, and temperature are the same. If I am talking about 2 different points on the PV space, their states have to be different. Maybe that pressure and volume is same, but at least temperature will have to be different then. Maybe that pressure and temperature will be same, but then at least volume will have to be different. Or maybe all 3 are different, or 2 of them are different. But any 2 distinct points on the PV space cannot have the same values of all 3 things, that is pressure, volume, and temperature. So that means any point on the PV space represents a unique state. It represents a state of a gas which has a unique value of pressure, volume, and temperature. Okay, so the state PVT can be represented as a point on the PV graph. Okay, for example, I have shown the points A and B, and any thermodynamic process from, let's say, an initial state, let's say like A I have shown, to a final state, okay, will be represented by a path, like path 1 and path 2. Okay, but in the case of application of first law, the value of delta U will not depend on the path. It will just depend on the initial position and the final position, that is A and B. So whether I'm going by path 1 or by path 2, the value of delta U will be the same for both of them, because both of them are represented by the same initial state and the same final state. So that is the meaning of a state function. That is the meaning of a quantity which is path independent. And delta U is such a quantity. The change in internal energy is path independent. It only depends on the initial state and the final state. So make a note of this first. Okay, now the next term we'll understand
Sir,
the
yes.
equation.
So, sir, can you please scroll up, please? For
Okay.
2 minutes. Yes, sir. Done, sir.
Okay, finished? Yeah. Okay, now next thing we have to understand is work done by the gas. Okay. So to understand this, let's look at a sort of experimental situation, like how we would actually achieve a thermodynamic process in an experimental setup. So for that, what we'd have to do is we'd have to have a container which has some kind of a piston. So this is a movable piston, and there is some kind of heating element through which we can supply or remove heat as and when whatever is required. Okay. So the gas which is inside this sort of a container is an ideal gas which currently is in a state P, V, and T. Okay. So if this piston has area A, then the force with which the gas is interacting with the piston, that is equal to the pressure into area. This is the force applied by the gas on the piston. Now, from here, suppose the gas is going into a state of expansion. So suppose what we are doing is we have a situation where this piston is now made to move up because the gas is expanding. So in that case, we can clearly see that the piston will be doing positive work on the gas. Or rather, the gas will be doing positive work on the piston. So if the piston is displacing like this through a distance x, we can see that the gas is undergoing an expansion process. Okay. The volume is going from initial volume of whatever this length was, L into A, to a final volume of L plus X into A. So you can see that the work done by the gas will be positive because F acts along the direction of displacement. With this force F that the gas is applying, it will be acting along the direction of the force, along the direction of the displacement. So for a small displacement, dx, this is changing by a small amount, dx. The work done by the gas for the small change will be f dx, okay, where dx will be positive. So the total work done by the gas will be integration of f dx, which becomes integration of p into a into dx. Now you can see that the volume of the gas at any point of time is equal to L plus X into whatever area. So a small change in volume is dx into that area because L is constant. Okay. So work done by the gas can be written as P into A into dx, which is nothing but integration of P dV. So this is the case where expansion is happening. So in an expansion, the work done by the gas will be positive. It will be a positive quantity. Whereas if we take the case of a negative change in volume or a compression, you can see integration P dV will become negative. So if we are going from the initial state like this, so after a while the state of the gas has become like this. So you can see that the change in volume is minus A into dx or minus A into delta x. So therefore work done by the gas, which will be integration P dV, will be equal to a negative quantity during a compression. Whereas during an expansion, the work done will be positive. So either way, the formula for work done by the gas is integration P dV. But whether dV is positive or negative, dV is positive for expansion. That determines that the work done is positive for expansion. Whereas dV is, the change in volume is negative when the gas is undergoing a compression. So that means work done becomes negative during a compression. Okay. So this is the quantity which is work done by the gas. Now just make a note of this, and we'll also see work done by a gas's interpretation on the PV graph, and you will understand that it comes from area under the graph, and therefore it is a path function. It's not a state function.
Sir,
Yes.
sir, can you just explain once again?
Yeah, work done का definition देखा है ना? You have understood work definition of work done by a force in work energy theorem, na? It is integration of F dx, Prince.
Yes, sir.
No, and it's positive when dx is in the direction of displacement. It is negative when dx is in the opposite direction. So that's what we are applying over here. So the work done by the force that the gas is applying, it is what? Integration of F dx. And F is nothing but pressure into area. So that's how integration of F dx becomes integration of P dV. Clear now?
Yes, sir.
So if the piston is going up because the gas is expanding, then we can see that the force applied by the gas will be doing positive work. Okay. Whereas if the piston is going down because the gas is compressing, then you can see the force that the piston is applying will be doing negative work, and dV will be a negative quantity because the change in volume will be negative. The volume is compressing.
Got it, sir.
Yeah, Diti, to answer your question from before, why pressure, volume, and temperature cannot be the same at all three cannot be the same at two different points, because any point on the PV graph now, any point represents a distinct value of pressure and volume. So it represents a distinct value of pressure, volume, and temperature. Okay. So for example, if I take another point which is lying on the same line vertically, it will have the same volume, but it will have a different pressure. So the moment it has a different pressure, it will have a different temperature. Similarly, if I take another point on the same horizontal line, it will have a different volume, but the same pressure. So it will have a different temperature, because the three variables are connected by this now. Now I can of course have the situation that P1V1 equal to nRT1 is equal to the product of some other pressure into volume, which is at the same temperature. Okay, but the pressures will be different, the volumes will be different, because they're two distinct points. Yeah, the volume will become L minus X into area. That's why I'm saying the change in volume, delta V, is minus K into delta X. The volume is going from L into X, sorry, L into area to a new volume, L minus X into area. So the change in volume, delta V, is negative. Yes, exactly, Chris, that's correct. If the gas is expanding, then work done by the gas is positive. Whereas if the gas is compressing in a certain process, then the work done by the gas will be negative. It's exactly opposite of work done on the gas. Work done on the gas is positive when the gas is made to compress, and work done on the gas is negative when the gas can expand. Okay, next let's understand the interpretation
Sir,
of
1
work done
minute.
in. Still not done.
Done, sir.
Done. Okay, next let's understand the interpretation of work done on the PV curve or the PV graph. So as we've seen earlier, any thermodynamic process can be represented by a PV graph, which shows a particular path from some initial state to some final state. Okay. So supposing for our particular PV graph, we are going from this initial state P1 V1 temperature T1 to a situation where the volume has expanded to V2. Suppose we are going by this kind of a path, then the work done by the gas will be integration of PdV along that path from the initial state P1 V1 to the final state P2 V2. So as you can see, at any intermediate time, if the pressure is P, the volume is V, then as it is going from V to V plus dV, so this thickness of the strip is dV. So work done by the gas is equal to PdV as the volume changes from V to V plus dV. Okay. So total work done, so that is the area of that strip, okay, which has a thickness equal to dV and a height equal to P. So the total work done, which is integration PdV from initial state to final state, is this total area under the PV curve, okay, which represents a given process. So this one over here, this is the PV curve for the given process from the initial state T1 V1 T1 to the final state P2 V2 T2. So in terms of the PV graph, the work done, which is integration PdV, It is represented by the area under the PV curve. So this is an important concept over here. So the next thing we'll see from this is that the moment we're talking about area under a curve, that means for two different curves between the same initial and final position or the same initial and final state, the work done will be different because the areas will be different. That means work done is not a state function. It is in fact what we call a path function. That means the work done depends on the path taken from the initial state to the final state. So unlike delta U, change in internal energy, which was path independent, work done is in fact path dependent.
Excuse me, sir. Can you? I have a doubt. Can you please explain? I mean that in this graph.
Sorry, come again, better. In this graph,
In this graph, there is one. There are two blue parts you have marked, and in between you made one red. I mean red marking. I didn't understand what is that. The DV wala part. Can you please explain that?
your pressure axis, right? This is your volume axis. This is your initial point where the pressure is P1, the volume is V1, okay? And therefore you have some temperature T1, which are related by P1, V1 is equal to nR T1, okay? So this is my initial state. Now from this, I'm going to a final state, which I'm assuming is somewhere here, where the pressure is P2, the volume is V2. So these blue colored lines are just to show me the guidelines that the value of pressure at this point, okay, is P2. The value of volume is V2, and those should give you the value of temperature, which is T2. Now the red colored curve, that's actually representing the thermodynamic process. To go from this initial state, let's say A, to this final state B, what is the path my system is taking? My system is taking this path, okay? So that's why I've said that this is the PV curve that represents the process from initial to final state. Is it clear now?
I'm asking about that. I mean the marking that you did in between P1 and P2.
Yeah.
From there you made one.
सर
I
वो
mean,
डीवी के बारे में पूछ रहे हैं सर वो
Okay.
डीवी
So
DV,
anyway,
yeah,
this
DV.
path is clear now. What it means by the path, right? This is the actual curve, which is the path that the system is following. Is it clear so far?
Sir, I'm asking about the DV. I didn't.
I'm asking, is it clear so
अरे
far? Up
इतना
to
सब
this
Yeah,
point?
so far, it's clear.
It's
Yeah.
clear.
Sorry.
Okay. Now see, while you're going from A to B along this path, you are suppose at some particular point. Okay. So what is the pressure at this point? It's the height of this line. That's the instantaneous pressure. And what is the volume at this point? Let's say it's V. So now these two are clear, what this is and what this is.
Yes,
right?
sir.
Now, when you move from this to a very close by point, what is happening? Your volume is changing by a very small amount, no? So it's changing by how much? It's changing by dV.
dV.
Okay, so dV is the small change in volume as you're going from the volume V to the volume V plus dV. Is it clear now what is dV?
Yes, sir. Got it.
Okay, so if I draw this small area, this strip, what is the area of this strip? It is length into thickness, no?
Yes, sir.
So the area of the thickness, area of the strip is equal to what? The thickness dV into the length. So that is P into dV. So what does this area of the small strip represent? It represents actually the work done while the volume is changing from V to V plus dV. So now if I put together all such strips, what is the net area? It is integration of P dV, area under a curve.
Got it. Thank you.
Understood? No? So this is basically the concept of definite integration. What does definite integration of a curve give us for the limit A to B? It gives us the area under the curve from A to B. So here, what is the function? It is the pressure. And what is the variable? Is the volume. So pressure integrated over volume, or the area under the PV curve, is nothing but integration P dV from initial to final state, or it's the definite integration of pressure into volume from initial state to final state. So what does that actually represent? It represents the work done by the gas. Okay, so that is what we mean now by the final statement, that integration P dV from initial to final is the total area under the PV graph.
Okay, thank you.
Okay, this point is clear now, 100%.
Yes, sir.
Okay, good. See, just like in kinematics, now before you studied the what is the area under the acceleration versus time graph? It is the change in velocity. What is the area under the velocity time graph? It is the displacement. If we have a velocity versus time graph for one dimensional motion, and your velocity is varying with time like this, so at a particular instant of time, if the velocity is v, okay, and at a new time, which is different only by a very small amount dt, so the new value of time is t plus dt. So from time t equal to t plus dt, okay, what is this area? It is v into dt. So what that represents? It represents a displacement. Okay, so that is why if I totally integrate from time t1 to time t2 over here, the total area, okay, becomes integration of v dt. That represents what? It represents the displacement from whatever time t1 to t2. So the displacement is the area under the vt graph from initial time to final point time. So just like that, the area under the pressure versus volume graph, what it represents the work done by the gas. So now additionally, we can see that because the work done is coming from area under the graph, so that means work done becomes a path function. Since W equals to the area under the PV curve for a given process, therefore work done depends on the path. Okay, so that's why we said that W is a path function. It is not a state function. Unlike internal energy, which was a state function and not a path function, because it is path dependent. Okay, and it's very easy to understand why it's path dependent. We can just visualize a PV graph with two possible paths. That means two possible thermodynamic processes, but both are connecting to the same initial and final point. If I'm going from A to B on the PV graph, but in one case I'm going by a path like this, let's say. So this is my path 1. So the work done will be this whole area now. So this whole area is A1. And now second time I repeat my experiment going from A to B, but by a different path like this, let's say. So for path 2, the work done will just be this area, which is A2. So you can see that work done by path 1 is not equal to the work done by path 2, but delta U in path 1 will be the same as delta U in path 2, which will be equal to NF by 2R into the temperature at the point B minus temperature at the point A. So it just depends on state, okay? Whereas work done depends on path. So this is a path function or path dependent function. Whereas this is a state function or path independent. Okay. Okay, so let's look at an
So-
example.
Excuse me, sir. Excuse me, sir. Please go down.
Not finished?
Yes, sir. Not finished.
Yes. Okay, done.
Are almost just 2 more, 1 more minute maximum. Done.
Okay. So now when it comes to the third term, which is the sum of delta U and W, the net heat supplied to the gas, it is equal to the sum of change in internal energy and work done. So this change in internal energy, this is a path independent term. Okay. Whereas work done by the gas we just now saw, this is a path dependent term. Okay. So if you're adding two things, one of them does not depend on path, but the other one depends on path. That means for two different paths, the value of Q will be different, because the second thing that you're adding, delta U plus W, for two different paths, your delta U is the same, but the W's are going to be different. So that means Q is also going to be different. Okay. So this implies that Q is a path function, or it is path dependent. Okay. Because as we were just visualizing, if I'm going from some initial state to some final state, but by two different paths, if I go by path 1, let's say Q1 will be equal to delta U plus W1, where W1 will be this whole area now. Okay. So W1 is area A1 and delta U is NF by 2R into temperature difference. But in the same thing, if I go by a different path now, if I go by this path, then this area being A2, Q will become different, because Q2 is equal to delta U plus W2. Okay. So W2, which is area A2, W2 is not equal to W1. Okay, which clearly means that Q2 is not equal to Q1, which shows that Q is path dependent. Okay, so this is the simple logic why Q is path dependent. So note this down and we'll quickly do an example problem. So a sample of helium gas initially at,
Sir, can you explain it again once?
sorry,
Can you explain it again once?
but there's nothing to explain. You just note this down. Q is delta U plus W. So you can see that it's just as the equation is given, the net heat supplied to the gas, it is the sum of the change in internal energy plus work done by the gas. Now change in internal energy we've just seen before, it's path independent, whereas work done is path dependent. So what about the sum of the two quantities? It will become path dependent. Okay. And the example I've given you, that if you go by the first path, you can see that Q1 is equal to delta U plus W1, where what is the value of W1? It's this area. Whereas if you go between A and B, the same 2 points, but by a different path too, your Q will become different. Why? Because the work done is becoming the new area. So the two work dones are not the same, because the two areas are not the same. So therefore you can show that Q2 is not equal to Q1, which is just proving the point that because Q is the sum of a state function and a path function, that means it becomes a path function, or it is path dependent. You know.
Clear, sir. Thank you.
Yeah. So sample of helium gas initially at pressure 2 atmosphere, volume of 4 liters, and temperature of 200 Kelvin undergoes a process as shown in the graph below to a final state of pressure of 3 atmospheres, volume of 6 liters, and temperature T2. Okay. So just start writing down. I'll explain the rest of the question. Okay, so I will just show the graph of the process below, so you can get started on the question also. So this question is accompanied by this diagram. Okay, which represents the PV graph for it. So the particular process that is shown in the graph, it is just a straight line like this. So this is the pressure P1, the volume V1, and this is the final state P2, V2. So first thing we have to do is we have to find the temperature T2. Okay. Find delta U. Okay, now for this, given that 1 atmosphere, you have to take as the approximate value as we've seen always, 1 into 10 raised power 5 pascals. Okay. Okay. So all these we have to find out for the process shown in the graph. Okay. So remember, it is helium gas which is going from this initial state to this final pressure and volume. The temperature you have to find out. Okay. So we will just be using the concepts we've learned about first law of thermodynamics till now. That is, delta U is the easiest thing because it's a state function. It only depends on initial and final state. So initial state is given to you in terms of all three things: pressure, volume, and temperature. Final state, two of the things are given, pressure and volume, but the third you can always find out by using the equation of state, because helium will be treated as an ideal gas. Okay. Then the work done is the next easiest thing to find out, because work done is represented by area under the curve. So here the curve is actually a straight line, so area is not difficult at all. Just find the area geometrically, and then Q will come from the statement of first law, that Q is equal to delta U plus W. Rest you have to just take care of the units and all that. Okay. So try this question out. So this is the most important section of thermodynamics for us in physics. Okay, maximum questions from this heat and thermodynamics section will be coming from here. Very few questions are from the thermal expansion part or the calorimetry part. kinetic theory of gases is important, but as you can see, kinetic theory of gases is more important from terms of application. Like this question also involves an application of kinetic theory of gases, because internal energies formula comes from KTG only, kinetic theory. Okay, so what is the value of temperature? How many people have got that? Very good. Correct, correct. 500 is the correct answer. Is it? Let's see. So for temperature, we have to just use a very simple relation that since PV is equal to nRT, okay, that means P1 V1 is equal to nRT1, P2 V2 is equal to nRT2. So in other words, the temperature will be equal to okay T1 into P2 V2 divided by P1 V1. So this temperature, initial temperature is 200. The pressure is changing from 2 to 3. So that's 3 by 2. And the volume is changing from 4 to 6. So that's another 3 by 2. So that's 9 by 4 times 200. So that's 50 into 9. So 450 Kelvin. That is the final temperature. Okay. So few people got it correct. Tantresh, Sitij, Unal, very good. Yash, Vashisht. Okay. Now once you got the temperature, actually technically you didn't even need the temperature because you could use PV equal to nRT for the second part. But first part of the question is directly about the temperature. So you got that. Okay. Now second part, delta U is equal to NF by 2R delta T by formula. Now here degrees of freedom will be 3 because it is helium, which is monoatomic gas. It's one of the noble gases. So delta U will be 3 by 2 nr into T2 minus T1. Now instead of finding the value of nRT2, nRT1, we can just replace it with 3 by 2 into P2 V2 minus P1 V1. Okay, because obviously nRT2 minus T1 is nRT2 minus nRT1, which is P2 V2 minus P1 V1. So this is a very useful trick in thermodynamics that anytime we have this kind of a relation, we can convert it into a relation for pressure. So it will be pressure and volume, that is. Okay, so 3 by 2 into, now this pressure is 3 atmospheres. So in SI unit, it is 3 into 10 raised power 5. The volume is 6 liters. So that will be 6 into 10 raised power minus 3. Okay. So the conversion factor we'll use is that 1 atmosphere is equal to 10 raised power 5 Pascal. That's been given in the question. And 1 liter is equal to 10 raised power minus 3 meter cube. So therefore 1 atmosphere into 1 liter becomes 10 raised power 2 joules. Okay, so this is the conversion you have to remember here. So this will become in fact 1800 joules. Okay, minus P1 V1. So P1 was 2 atmospheres and V1 was 4 liters. So this calculation that we get finally will be in joules because I've converted to SI units. So you can see it is 3 by 2 into 1800 minus 800. So that's 3 by 2 into 1000 or 1500 joules plus 1500 joules. That is the change in internal energy. The internal energy is increasing by a factor of 1500 joules. Okay, so let's see who all have got this correct. Yeah, Prince. Okay, other people. Kunal has made some mistake with unit, otherwise you got it correct. Actually, yes, yours is also conversion mistake. Okay. Okay, now what about the work done? How we will calculate the work done? Work done will be this total area under the graph. Okay. So just see how you can geometrically calculate the area under the graph. Always. Okay, very good. Now let's calculate the work done. So as I said, for the work done, we have to just use the formula of area under a trapezium or area of a trapezium to calculate area under the curve. Okay, so you can see it's an expansion. So W will be positive of the area. Okay, so the area is half of sum of parallel sides, okay, into perpendicular distance between them. Okay. So you can see that this trapezium is like this. This side is P1. Okay. This side is P2. And this perpendicular distance is V2 minus V1. So this will become half of P1 plus P2
Sir, we can
into
make it
V2
square,
minus.
rectangle plus triangle also, no?
Yeah, you can do it rectangle plus triangle. You will just end up proving the formula that for trapezium this is the area. So anyway, so half of now the sum of the pressures. The pressures were how much? 2 liters. Sorry, 2 atmospheres and 3 atmospheres, right? P1 and
Yes, sir.
P2 were 2 and 3, and V1 and V2 were 4 and 6. So 6 minus 4. So this is in liter. This is in atmosphere. So this will give us, okay. So this will be in atmosphere liter. So when we convert it, become 500 joules. So plus 500 joules is the work done by the gas. Okay. So now we've already established that delta U was how much? 1500 was it? Yeah, plus 1500. And now we've just seen that work done is plus 500. So change in internal energy, heat supplied Q that will become this 2000 joules. So that means 2000 joules of heat are supplied to the gas, out of which, okay, out of which 1500 gets stored in the gas as the change in internal energy, whereas 500 are expended in the process of the gas doing work. So this is the meaning of this, that 2000 joules of heat are supplied to the gas. Okay. And out of this 2000, 500 joules is the work done by the gas. And the remaining 1500 joules is the increase in its internal energy. Its internal energy increases by a factor of 1500 joules. The gas ends up doing mechanical work on its environment because it expands of 500 joules. And that's how the 2000 joules to the gas are ultimately used. Okay, so having understood this question, next we will look at.
Sir, can you please load it up?
Right.
Sir, please load it up.
Right.
Four.
Sir. Sir. Sir.
Yeah.
Sir, can you show the result of the triangle plus rectangle one area?
Arey, so what is there in that? Yeah, this you're breaking this
Sir,
into a
answer
rectangle
is
like
not coming. That's why.
तो it will come ना देखो ये P1 है और ये same distance D है ठीक है so this is the rectangle and then the triangle is this one on top its base is D only and this height is how much P2 minus P1 na
Yes, sir.
so how much will be the area it will be the area of the rectangle let's say A1 plus the area of the triangle let's say A2 so that is P1 into D plus half into base into height so that is P2 minus P1 into D. Okay, so now do this calculation. See, it will come out to be half of P1 plus P2 into D, which is the same formula as this. No difference, no, at all.
Sir, while directly putting the values in the
अरे तो कुछ
question.
मिस्टेक किया होगा ना बेटा चेक करना ये D कितना है देख यहाँ पे ये वॉल्यूम का डिफरेंस कितना है टेल मी it's 6 minus 4 2 liters this pressure P1 is how much P1 is how much 2 atmospheres so this is in fact becoming a like if you take equal values it's a square so this one's area is how much 4 liter
Yes,
atmosphere
sir. Yes, sir. I guess.
okay. And then the triangle this pressure difference is how much this is 3 liters this 2 liters so this sorry 3 atmospheres so this is 1 atmosphere and this is 2 liters okay. So this one's area is how much half of 1 into 2 that's 1 liter atmosphere so total is coming to 5 liter atmosphere
Yes, sir. Sorry.
okay so we'll
Sir,
quickly
just a
see one or
second.
okay.
Done, sir.
Okay. Okay, now next part of thermodynamics that we'll be seeing is something you're familiar with from chemistry again. We'll be seeing the 4 standard processes. Okay. The 4 standard type of processes. Namely the isobaric, isochoric, okay, adiabatic and isothermal. This is a process where volume is constant. Isobaric, this is a process where pressure is constant. Okay. Isothermal is a process where temperature is constant. And adiabatic, there is a process where heat is zero, heat exchange is zero. Or we can also say like this, that the change in volume is zero because volume is constant. The change in pressure is zero. The change in temperature is zero. So to each of these, we will be doing the application of first law. So for example, let's start with isoporic process today. So first of all, if volume is constant, it means that pressure is proportional to temperature because PV is equal to nRT. If volume is constant, you can see that pressure becomes proportional to temperature. So this type of process on the PV graph will look like a vertical line because the volume axis is the horizontal axis. So this is represented by this kind of a path when it is isoporic. You can see that pressure at B is greater than pressure at A. So that implies that temperature at B is greater than temperature at A, but volume at A is equal to volume at B, which is whatever this volume is, let's say V1. So therefore we can say that A to B, if we went in that direction upwards, that would be a isoporic heating process because the temperature would increase. Okay. Whereas B to A, if we went from the point B to the point A downwards, it would represent a isoporic cooling because the temperature is reducing. Okay. Now let's look at the application of first law. Okay. Now W is equal to integration P dV. That becomes zero because you can see that volume is constant. That means the change in volume is zero. Or you can see from the graph that area is zero because it's a vertical line. So that's the first thing. In an isoporic process, the work done by the gas is zero. Delta U, of course, is given by the standard formula NF by 2R delta T. So this is the same for all processes. There is a state function. So it's a common formula for all processes. But now what happens that W is zero means Q is equal to delta U equal to NF by 2R delta T. So this is the whole thing about the isoporic process. This is the full application. So this Q is written as a specific term now. So Q is written as NCV delta T, where CV is molar specific heat capacity at constant volume. Okay. So what we mean by molar specific heat capacity is the heat required to raise the temperature of 1 mole by 1 Kelvin at constant volume. That is the definition of CV. Okay, so if we connect this definition of CV with what we have learned about this process from the application of first law, so we can see that therefore Q equal to delta U for isoporic process implies that NCV delta T equals to NF by 2R delta T. So you have the standard formula which you know that CV for any gas is F by 2R. Isoporic molar specific heat capacity CV, it is 3 by 2R for monoatomic gases. and it is 5/2R for diatomic gases. Okay. So all the important information that you need to solve anything related to an isophoric process, you can see is over here. The formulae are here, the graph also is made, so whatever graphical analysis is required that you can do. Okay. But most importantly, to remember that W is 0 for isophoric because the volume is not changing, and therefore Q is equal to delta U. So that also shows you that Cv is equal to F/2R. Okay, so people, with that we will conclude today's session. Next lecture we will look at the application in the other 3 standard processes and then numerical problems related to that. Okay. Yeah, you can solve kinetic theory of gases completely from H.C. Verma. You can also start with the questions from the next chapter, which is First Law of Thermodynamics. Okay, because you've understood the fundamentals of how to calculate W and delta U. So any process you can apply that to. W comes from either integration PdV or area under the graph. Okay, and delta U has that standard formula. Okay, so hope this is clear, people, so far. Okay, so that's it for today's class, people. Wish you all the best.
Bye, sir. Thank you, sir.
Thank you, sir.
Yes, okay.
Bye, sir. Thank you, sir.
Bye.